All right, this lesson is going to be a little less than ideal, but since I'm not here in class today, it's going to be the best that I can do. The first thing we got to do is talk about what soluble and insoluble means. So when we talk about something being soluble, that means it will dissolve. So like sugar is soluble and salt is also soluble. But truly we ought to say soluble in what? If someone just says something is soluble, they probably mean soluble in water. But in a lot of cases, things aren't soluble in water, but they would be soluble in something else. Like if you've ever gotten like pine tar or something like that on your hands, you know that you can go and get a little bit of gasoline or some Goo Gone and it'll dissolve in that, but it's never going to come off in water. So technically speaking, we should say in what, but if you don't, you can assume in water. Insoluble is the opposite of that. And when we talk about things being insoluble, that means probably water unless we say otherwise. So when ionic compounds, soluble ones, when they dissolve in water, become aqueous, what happens is those ions separate. So while magnesium sulfate is written MgSO4, when you put it in water, what it actually looks like is the magnesium ions are pulled apart and separated. We call this dissociated from the sulfate ions, and the water molecules around them separate them from each other, and they stay separate in this solution. This is what aqueous magnesium sulfate actually looks like. Sodium hydroxide over on the other side, if it's aqueous, we see that the sodium ions are separate from the hydroxide ions by the water molecules. Now, it's worth noting that the way the water molecules are oriented is important. Remember that Mickey Mouse's ears are positively charged in the polarity of a water molecule. That's the positive end of the water molecule. So those positive ears are going to be attracted to the negative ions. So we see around the sulfate ions here that it's always the positive ears of the water molecule that are touching the sulfate ions. Similarly, the chin of Mickey Mouse, the negative side of the molecule, the oxygen is more electronegative, so it pulls the electrons that way. That side is touching the positive ions. That's a little detail, but it's an important detail, and that might show up on an assessment at some point in the future. So I think that's worth mentioning. But in any case, this is the picture we have in our head of these two things when they're separate from each other. So what we're going to do right now is we are going to make a YouTube video of another YouTube video that I made. This is going to be kind of trippy. Maybe it's not going to be kind of trippy. I don't know if it's going to work with the screencaster playing. It may not. Hang on. We're going to try it quickly. Well, oh, here it is. All right, what we have here are two beakers, each containing dissolved aqueous ionic compound. In the beaker on the left, we've got magnesium. Oh, you can tell this guy knows what he's talking about. Yeah, but it's not water. This is kind of like Inception. It's like a video within a video. Me within me. Oh. Yeah, actually, and I should have let that sit and taken a quick picture of it afterwards to show you what that looks like. But that precipitate would settle out of there and end up in the bottom. So what do we imagine is going on there? Well, here's the reaction, okay? We had that magnesium sulfate, it was aqueous, and we had the sodium hydroxide, it was also aqueous. When they were separate from each other, the magnesium had only ever bumped into sulfates and other magnesiums, and so it never did any reactions with those. And the sodium and the hydroxides were separate. They never bumped into anybody else. But when you dump them all together, all of a sudden, what can happen is the magnesium, who's never bumped into anybody at sulfate until now, all of a sudden bumps into hydroxides. Similarly, the sodium sees sulfate for the very first time, and some of these times there's going to be a reaction that occurs. It turns out that magnesiums bump into hydroxides and make this solid right here, magnesium hydroxide. That is the precipitate that we saw, that white cloudiness in that beaker. And the sodium sulfate stays aqueous. And well, how would you know what's going to do what? You need these rules. Now, don't write this down. Morgan, put down your pencil. I'm watching you. Kaylin, stop it. The ions in any compound are listed in one of these rules here, and it gives you some idea about whether those things would be solid or not. So you read through these. This is in your homework. It's in lots of other things that we're going to be using for the rest of this unit. You don't need to remember these. You just have to know how to use them. So you should have that stuff out. It might be handy here in the next minute or two to have this stuff out. So as we look at this reaction, what we do is we take this reaction. We're going to actually write two other reactions from it. Okay? We are going to see that everything that's aqueous, like the magnesium sulfate, we're going to take and we are going to write what's called a full ionic equation for this. All the aqueous things are going to get split into the ions that make them. So in magnesium sulfate, there is a magnesium ion and a sulfate ion. We write them separately, the plus sign in between them, and these are aqueous. Okay. Also, the sodium hydroxide was aqueous in the beginning. So we're going to take actually two sodium hydroxides. So two sodium hydroxides, the two here, becomes two sodiums and two hydroxides. Okay, we split all those ions up. Okay, and then we go over to the other side. We see sodium sulfate. Is going to be in sodium sulfate. We find that there are actually two sodium ions, and there's one sulfate ion. And so that's the end of our aqueous components. We had aqueous magnesium sulfate, aqueous sodium hydroxide, aqueous sodium sulfate. This magnesium hydroxide is a solid. Anything that's a solid, we're going to write just like we had it in that equation. It's combined together. Solids actually are stuck together. So the magnesium is actually stuck to the two hydroxides. They're together. The other stuff is dissociated. Those ions are in the solution separated by water. And so what the full ionic equation is it's really like a more accurate way, a more complete way. It's a lot bigger way too, and a lot more work to write what's actually going on here. Okay, so then what we do when we write the net ionic reaction is we go through here. Let me clear the ink off of this page. Actually, I don't see my button right now. Oh, there it is. Clear ink. So what we're going to do now is we're going to look at this reaction, the full ionic reaction, and we're going to remove what are called spectator ions. Spectator ions are ions that don't do anything in the reaction. They are unchanged. They look the same on the left side of the reaction as they do on the right. Look at that sulfate ion. It's on the left, it's aqueous. On the right, it's aqueous. It didn't do anything. And the same thing with those two sodiums. They didn't do anything either. They're spectators. They're the worst kind of spectators too. They don't even cheer. So we get rid of those and we write what's left over as the net ionic equation. If you've done a good job of balancing your chemical reaction in the first place, like we did here, we put the 2 in front of the sodium hydroxide. That should carry through, and at the end here we should find that we have a balanced chemical equation still. So we have 1 magnesium, and then we have 2 oxygens and 2 hydrogens. So 1 magnesium, 2 oxygens, and 2 hydrogens. It is still balanced at the end. If you did a good job up until this point, it should still be balanced when you get to the end. Let's do some more practice of like this. And you might find it helpful to pause the video and just look at this for a while before we move on. Okay? So here are the steps. Again, don't write this down. Lily, put the pencil down. I'm watching you. These steps are here. They're on the website. You can find them anytime you want to. I just like practice, just jumping into this thing. So what we're going to do here is we are going to first predict the products of this double replacement reaction. So we are going to take the positive ion from the one compound and put it with the negative ion from the other compound. In this case, that is going to be an aluminum ion. Aluminums are +3 ions. Are going to go with this phosphate ion. A phosphate ion is a -3 ion. That sounds like it's going to be real cute. And the positive ion from this compound is going to go with the negative ion from that compound. The sodium with a +1 charge, that's the charge of a sodium ion, is going to go with chlorides. Those are -1 ions. This is going to be real cute. So when I go over to the other side, sodium chloride is just going to be 1 sodium and 1 chlorine. And aluminum phosphate is going to be 1 aluminum and 1 phosphate. We're going to write those products. They're going to look just like that. Okay? So now what we're going to do is we are going to balance this reaction if we need to. And I think we do. As I look here, I see 3 sodiums on the left, but only 1 on the right. I see 3 chlorides on the left, but only 1 on the right. We can solve that pretty easily by putting a 3 in front of the sodium chlorides. Okay? Now I get out my solubility rules. And those solubility rules, they're really great. They even help precipitate. We are going to find that the sodium chloride, if you look at rule number 2, it says almost all salts of sodium are soluble. Rule number 3 says all salts of chloride are soluble with a couple of exceptions. Sodium chloride, friends, is going to be aqueous. We actually know that from our everyday experience. Salt, like that's table salt, dissolves in water. Okay. And then we go looking for aluminum and phosphate. I don't see anything in the rules about aluminum really anywhere. But phosphate comes in rule number 7. Salts containing blah phosphate, blah, 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 are insoluble except when they contain ammonium or an alkali metal. That means that aluminum phosphate, since aluminum is not ammonium and aluminum is not an alkali metal, aluminum phosphate is going to be a solid. So now we go through and we write that big nasty equation where we break all the aqueous things up. The aluminum chloride is 1 aluminum and 3 chlorides. The sodium phosphate is 3 sodiums and 1 phosphate. 3 sodium chlorides are 3 sodiums and 3 chlorides, and the aluminum phosphate is a solid, so it doesn't get broken up. It stays together. Now we get rid of spectators. Look at that. The chlorides and the sodiums are going to fall right out of here, and we write what's left over. This is our net ionic equation. So we have what's called a full molecular equation is the first one. The full ionic equation is the second one, and then the net ionic equation is the third one. Okay, let's do this again. I'm going to try and pick up the speed because I'm going to run out of time here. I can only make a 15-minute video. I'm already 11 minutes in. Woo! So, aluminum chloride and sulfuric acid. Let's double replace here, okay? So the aluminum ions are +3 charged ions. This is the part that is so easy to screw up, and if you goof up step number 1, you are never coming back, friend. And sulfates are -2. So since aluminum is +3 and sulfates are -2, when I get them together, I need 2 aluminums to go with 3 sulfates, okay? And then hydrogen ions, we know this is going to be an acid. Hydrogen ions are +1s and chlorides are -1s, so HCl is just 1 hydrogen and 1 chlorine. Okay, you got to double replace correctly. That is the most common place to screw up, and if you screw up the first step, you might as well not even go on with the rest of it. So we've got our compounds there. Now we get out actually we balance this thing. I can see that we are not balanced. We're going to throw a whole bunch of coefficients in here. 2 aluminum chlorides, 3 sulfuric acids, gives me 1 aluminum sulfate and 6 hydrochloric acids. Now I find my state symbols by looking at my solubility rules. Aluminum sulfate, there's nothing in here about aluminum. Rule number 6 says most salts containing sulfate are soluble, with some exceptions. Aluminum sulfate is going to be aqueous. And rule number 1 says all acids are always soluble, so that's always aqueous. Friends, this is a joyous occasion. We have mixed 2 aqueous compounds and produced 2 aqueous products, which means absolutely nothing happened. Can't see anything in this beaker, nothing cool. Nothing happened, no reaction. We are done. Let's move on and doing that. Try and squeeze one in here in a minute and a half in order to get more practice with this. So we are going to double replace lead and potassium, lead 2 nitrate and potassium iodide. The potassium and the +1 ion and the nitrates of a -1 ion, that makes potassium nitrate look like that. The lead must be a +2 charge. I can tell because it's with 2 nitrates. So this is a lead 2. And it is going with an iodide. Iodides are -1 ions, so when I make lead 2 iodide, it looks like that. Okay, so we've got our products done. We are now going to balance this reaction by placing some 2s in. And then after we do that, we get out our solubility rules. Rule number 5 says all salts containing nitrate are soluble. Rule number 2 says all salts containing potassium are soluble, so potassium nitrate will be soluble. But number 3 says that the lead 2 iodide will be an exception, and that iodine is going to make that insoluble. So potassium nitrate is aqueous, but the lead 2 iodide, rule number 3, says salts containing iodide are soluble except those with lead 2. So that's going to be a solid. Wah, wah, wah. So we bust up all the aqueous stuff. The lead 2 nitrate contains a lead 2 ion and 2 nitrate ions. The 2 potassium iodides are 2 potassiums and 2 iodides. The 2 potassium nitrates will be 2 potassiums and 2 nitrates. And the lead 2 iodide is a solid. We just rewrite that the way it was. We get in here and we cross out our spectators. And we write what's left over as a net ionic equation. I have got 35 seconds left. We're going to do one more. Iron 3 chloride, mixed sodium hydroxide. We're going to double replace the mixed sodium chloride and iron 3 hydroxide. Then once we've got that, we are going to put 3s in there to balance the reaction. We're going to get our solubility rules out, and we're going to find that sodium chloride is going to be aqueous, but iron 3 hydroxide is not going to be aqueous. So we split up all these components into the ions that make them. We take them one at a time, working our way slowly across the thing, and we end up with this. We cross out our spectators, and we have a final reaction that says iron 3 mixes with 3 hydroxides and make iron-free hydroxide. That's the end. I hope this helped. Goodbye.